Let us start the class today. In the previous period, we have studied about the liquefaction of gases. We have studied that gases are liquefied under certain temperature. This temperature is known as the critical temperature. The pressure at which, or the um, lowest pressure at which the gases can be liquefied at critical temperature is known as critical pressure, and the at critical pressure and critical temperature, volume of 1 mole of gas is known as the critical volume. We have seen that boil point is the point at which a gas behaves like, or a real gas behaves like an ideal gas for a long range of pressures. We have even seen that we can, when we liquefy the gas below critical temperature, all gases can be easily liquefied. And this liquefaction of gas is possible uh, only under critical temperature. So for all the temperatures below critical, for all the temperatures below critical temperature, you can see that the gas can be easily liquefied, and we can see we get a dome like shape here. So for the temperature below critical temperature, that is 13.1 for carbon dioxide and 21.5 degrees centigrade, you can see that we get a line parallel to the volume axis. This is where there is an equilibrium between the gas and liquid, and at any volume outside the dome and left side portion, the gases are liquefied. So this lines what I'm shading is the condition where gas exists as a liquid. When a complete volume of gas has been converted to liquid, you can see that we get a steep slope, and this steep slope represents that whatever pressure we have been applying, that pressure is utilized to compress the liquid, and that is why the change in the volume is very small. Same way, we have even seen that we can directly convert gases into liquid without passing through this green region. So for that, we move from A to F, then from F to, we move along the 31.1 degree centigrade temperature curve, and we reach the point G, and then from point G we move towards D, and when we cross this H, the gas simply liquefies. So this is how, my dear students, we have studied about the liquefaction of gases. I hope you understood it well, and you found it interesting. Now, moving forward, my dear students, we should study more about the same topic. So let's begin today's class. We have even studied about the permanent gases, that gases which shows continuous positive deviation in Z value are called the permanent gases, and these permanent gases are hydrogen, nitrogen, and helium. So they are known as the permanent gases. Liquefaction of so-called permanent gases, that is gases which shows the continuous positive deviation in Z value, requires cooling. So if we want to convert these permanent gases to liquid, we have to cool. Apart from cooling, we need to even compress them. We need to increase the pressure for their liquefaction, and compression is very necessary in these particular cases. So in case of such gases, cooling is highly needed. Next, note liquefaction. Okay, why do so-called permanent gases? Why do so-called permanent gases requires cooling as well as considerable amount of compression? So yesterday, even in the previous class, we have seen that just by decreasing the temperature, we just um, make their movement slower, and when we compress them, the gaseous molecules come closer in a close vicinity, and these intermolecular interactions hold these gases which are closely packed, or they are close to each other, and they are moving slowly, and that is how the liquefaction is possible in an easy and simple manner. My dear students, we have even seen yesterday that we can it is possible to change a gas into liquid or a liquid into gas by process in which uh, they remain always in a single phase, and we have seen that how we can move from A to F, and then along the axis 31.1 degree centigrade we reach the point G, and when we reach point G we go towards D, and by doing that when we cross H the gases can be liquefied. Now, my dear students, we want to study about the fluids or the liquid state. So, anything that can flow is called fluid. Both gases and liquids are called fluids. So, you might have studied in ninth standard, even my dear students, that anything that can flow is known as fluid, and gases and liquids both are known as fluids. Only below critical temperature, both the states, liquid and gas, is possible. So, below the critical temperature, we can have both the states simultaneously, that is, gas and liquid. Above critical temperature, only gaseous state is possible. So that is what we can easily understand, that above critical temperature the gases cannot be liquefied, and that is why above critical temperature only gaseous form is possible. So above critical temperature, my dear students, that is the temperature of 13.91 degrees centigrade, carbon dioxide can be called gas. But below critical temperature, we should say carbon dioxide, not gas, but it is vapor. So this is the difference between the gas and the vapor. The existence of gas under its critical temperature is known as vapor. So below 30.91 degrees centigrade, we will call carbon dioxide gas as not gas, but we will call it carbon dioxide vapor. At critical temperature, liquid passes into gaseous state imperceptibly. Imperceptibly means in such a way that we cannot notice that gases are converting into liquid and liquid are converting into gas, and they are converting themselves continuously. So the surface separating two phase disappears. Please remember that at critical temperature, what happens? The surface that separate the gaseous state and liquid state disappears. So we have seen the graph that in the green shaded region, the graph, both liquid and gas coexist, and they have surface separating two phases, which was visible. Now we'll move, my dear students. Now we have a problem. Gases possess characteristic critical temperature which depends upon the magnitude of intermolecular forces between the gas particles. So critical temperature depends upon the intermolecular forces between the gas particles. Critical temperature of ammonia and carbon dioxide are 405.5 Kelvin and 304.10 Kelvin respectively. Which of these gases will liquefy first when you start cooling from 500 Kelvin to their critical temperature? You know, we start cooling these gases, and which gas do we expect to cool or to liquefy first? So let's answer this question. Gas with higher critical temperature will liquefy first, because when you cool them, the higher temperature comes first, and that is why the cool ammonia will liquefy Ammonia will liquefy first because its critical temperature will be reached first on cooling. So liquefaction of CO2 will require more cooling, whereas liquefaction of ammonia will be first or faster than the liquefaction of carbon dioxide. Please note that at 1 atmospheric pressure, carbon dioxide gas cannot be liquefied. Please remember that carbon dioxide gas cannot be liquefied at 1 atmospheric pressure, and that is why at 1 atmospheric pressure, carbon dioxide gas generally sublimates. That means from gas it directly turns into solid, or from solid it directly turns into gas. This is how, my dear students, we understand the behavior of carbon dioxide under the change into the pressure. Now, my dear students, we have completed our 11th start discussion about the gaseous state, and now we want to study about the liquid state. So let us study about the liquid state. Let us study the various properties of liquid states. Intermolecular forces are stronger in liquid state as compared to the gaseous state. So next, it's quite easy to understand. Intermolecular space is less in liquid as compared to gas. Thus, in normal condition, liquids are denser than the gases. The density of liquids are generally, in normal condition, uh, density of liquid has more than the density of gases. Liquids have definite volume, that you might have seen that a 2 liter water remains 2 liter itself. It does not change its volume because molecules of liquid do not separate from each other, and that is why their volume is definite. You may be asked this question, that why do liquids have a definite volume. You can simply answer this, that liquids have definite volume because molecules of liquid do not separate from each other, and that is why they have enough force of attraction to maintain their volume. Liquids can flow because, now this reason may be asked, that give reason why liquids can flow. So you can even learn this. Liquids can flow because molecules of liquids can move past one another freely. See, these molecular liquids are available, molecules of liquid. This layer and this layer, they move past one another, and that is why the liquid can flow. So they forms layers, and the layers of molecules can move past one another, and that is why liquids can flow. Liquids do not have fixed shape. Liquids can be poured. You can pour them from one vessel to another, and when you pour them from glass to the cup, then the shape changes, and initially the liquid was having the shape of the glass, which turns to be the shape of the cup, and liquids take the shape of the container in which they are filled, or they are stored, or they are poured, whatever you understand. Following are the important physical properties of liquid. First is vapor pressure, another is surface tension, and third one is viscosity. My dear students, these three properties of liquid we are going to study in detail in this chapter. So first we want to study about the vapor pressure. I hope, my dear students, you have this figure on your screen. बच्चों, आप सबको ये फिगर दिख रही है क्या?
Yes, sir.
Okay.
Yes,
So
sir.
let me explain this figure for you. What happens? We take a closed container. Remember, the container is kept closed. In this closed container, my dear students, we feel the liquid. This is the liquid that we feel in it. When we feel the liquid, initially there was no vapor of liquid available. And this portion of liquid is known as the surface. That is what we are all aware. This is surface of the liquid. Now what happens, as the time passes, after some time what we see, that the liquid turns into vapors, and you can see here these small vapor molecules available. These vapor molecules start applying pressure on the surface of the liquid as well as on the wall of the container. Please remember that as soon as the liquid start converting into the vapor molecules start colliding with the wall of the container, and this is how they exert the pressure on the wall of the container. This pressure what they exert on the wall of the container, we start calling this pressure as a vapor pressure, because the pressure exerted by vapor molecule, and that is why it is known as the vapor pressure. Now what happens, the liquid start converting to vapor. Same way, after some molecules, when they turns into vapor phase also start going into the liquid phase. So now two-way process starts, that vaporization and condensation takes place simultaneously. Vaporization takes place, so liquid goes to the vapor turn condense to the liquid, that is what it is, condensation. So both vaporization and condensation takes place simultaneously here. But at one particular stage, a stage is reached when the number of molecules going from a liquid to vapor stage and the number of molecules going from vapor state to liquid state, they become equal. That particular condition is represented as equilibrium. So at this equilibrium, what happens? The vapor pressure become constant or it become maximum. The vapor pressure become maximum as well as constant. So now the vapor pressure does not change anymore. The pressure become constant, and at that time this liquid at given temperature shows the maximum vapor pressure. This vapor pressure is the vapor pressure of liquid that we have given. It is also known as the equilibrium vapor pressure, and this is the equilibrium vapor pressure or vapor pressure at equilibrium or maximum vapor pressure we are going to study about in detail. Whatever I have explained, my dear students, that we are going to read into the text. So if you do not understand anything, you can ask me immediately. If an evacuated container is partially filled with a liquid, remember we need to fill it partially. We are not going to fill it completely so that the evaporation takes place. A portion of liquid evaporates to fill the remaining volume of the container with the vapor that we can see into the figure number 2. The liquid evaporates and pressure exerted by vapors on the wall of the container as well as on the surface of the liquid called vapor pressure. We have seen that in the second figure that the vapors have started applying pressure on the wall of the container as well as on the surface of the liquid. Such vapor pressure increases as the evaporation increases. So, my dear students, as the evaporation increases, this vapor pressure also increases. The molecules of vapor collide with one another as well as and liquid molecule and get condensed. Now, what happens? These molecules, they collide with each other at the same time. They collide with the liquid molecules and they also condense. So, condensation also start. The vapor molecules also start converting into the liquid. So, evaporation and condensation takes place simultaneously. So now in figure 2, if we have seen that both the processes, evaporation and condensation, started simultaneously into the closed container. That's what we understand. Now what happens? A time comes when the molecules a time comes when the molecules evaporated and molecules condensed become equal. That means the number of molecules going into the liquid phase to vapor phase and vapor phase to liquid phase become equal. Vapor pressure, that is the pressure exerted by vapor on the wall of the container, shown in green arrows in figure 2 and figure 3, become constant. So at what happens when the molecules going into the vapor to liquid and liquid to vapor become equal, the vapor pressure become constant. We say an equilibrium is established between the liquid phase and vapor phase. So we can see that at that time we call it as an equilibrium between the liquid phase and vapor phase. And vapor phase, when equilibrium is established, vapor pressure, when equilibrium is established between liquid phase and vapor phase, is known as equilibrium pressure, or saturated vapor pressure. So if you are asked the definition of equilibrium pressure or saturated vapor pressure, you can write this definition that vapor pressure when equilibrium is established between the liquid phase and vapor phase is known as equilibrium vapor pressure or saturated vapor pressure. Sometime you may be asked, so it's better you learn this definition and you understand it well. Since the process of vaporization is temperature dependent, the temperature must be mentioned while reporting the vapor pressure of a liquid. So, vaporization depends upon temperature. So, when we are mentioning the vapor pressure of any liquid, we need to mention at what temperature the liquid exerts that much of vapor pressure. It is very much necessary to mention this, my dear students. So please keep in mind. And now if you have any doubt, anything which you could not understood, you can ask me. बच्चों अगर कुछ समझ में नहीं आ रहा है तो पूछ सकते हैं या फिर हम आगे चलते हैं. कुछ ऐसा है जो समझ में नहीं आया तो पूछ लीजिए प्लीज. आप लोग मुझे सुन पा रहे हैं?
Yes, sir.
तो कुछ समझ में नहीं आया या सब कुछ समझ में आ गया है? ओके, चलिए आगे चलते हैं. यू विल नॉट आंसर, आई होप. व्हेन अ लिक्विड इज when a liquid is heated in an open vessel. Now, please remember, until now, whatever it was the discussion for closed vessel. Whatever we have discussed, that we have discussed for the closed container. Please remember that now we are going to study, or whatever the discussion is there, it is the discussion for the open container. So when a liquid is heated in an open vessel, the liquid vaporizes from the surface. See, we are thinking of the open container. Please remember that the liquid vaporizes and it goes into the open region. A temperature at which vapor pressure of the liquid is equal to the external vapor pressure or atmospheric pressure. Vaporization can occur throughout the bulk. So just have a look to this. This is the surface of a liquid. Here we have a liquid. This liquid generally turns into vapor. But vaporization is a surface phenomena. So vaporization takes place only at the surface. That means the molecules present over here, they only vaporize. All the liquid does not vaporize. But then, they also generate a pressure on the surface due to vapor. This pressure is called vapor pressure. And this vapor pressure is equal to atmospheric pressure. Whatever the atmospheric pressure and this vapor pressure become equal, the vaporization starts into the bulk. This region, what we can see here, this is what it is known as bulk. So the molecules from the bulk also start converting into the gas. This condition we call it as a boiling. So when the vaporization takes place into the bulk apart from surface, that particular condition is known as boiling. So whenever there is a boiling, my dear students, the vapor pressure of a liquid is equal to the vapor pressure of atmosphere or vapor pressure exerted by the air present around it, because we have the open container. And in that condition, vaporization can occur throughout the bulk of the liquid and the vapor expand freely, and the vapors expand freely into the surroundings. Now, the condition of free vaporization throughout the liquid when vapor pressure is equal to the atmospheric pressure is called boiling. So please remember that this condition, when the vapor pressure is equal to atmospheric pressure, we call that condition as a boiling. The temperature at which vapor pressure of liquid is equal to the external pressure is called boiling temperature or boiling point of liquid. So please remember that at the temperature at which the boiling start, that means the vapor pressure of given liquid is equal to the atmospheric pressure. This temperature is known as the boiling temperature or boiling. Now, boiling point can be of various type. So this boiling uh, this boiling point can be of various type. We have two different types of boiling point. First one is known as the normal boiling point, and another one is known as the standard boiling point. Remember, we have two type of boiling point. First one is normal boiling point, another one is standard boiling point. At 1 atmospheric pressure, boiling temperature is called normal boiling point. So when the temperature is 1 atmospheric, the boiling point is normal. But when the temperature is 1 bar, at 1 bar pressure, sorry, at 1 atmospheric pressure, the boiling point is normal boiling point. At 1 bar pressure, the boiling point is called the standard boiling point. At 1 bar pressure, at 1 bar pressure, boiling point or boiling temperature is called the standard boiling point of the liquid. So this is how, my dear students, we can understand about the two different types of boiling points. Please remember that 1 bar is considered as a standard pressure, and that is why at that temperature the boiling point, at that pressure the boiling point is known as the standard boiling point. Now we have a reason to understand, give reason. Standard boiling point is slightly lower than the normal boiling point of the liquid. Why standard boiling point is slightly lower than the normal boiling point of the liquid? The reason is very simple, because 1 bar pressure is slightly less than the 1 atmospheric pressure. So 1 bar pressure is slightly less than the 1 atmospheric pressure, and that is why it happens. 1 atmospheric pressure is equal to 101.325 kilopascal, or you can say 1.01325 into 10 to the power 5 pascal, whereas this 1 bar pressure is simply 10 to the power 5 pascal. So this is how you can easily understand that 1 bar pressure is slightly less than the 1 atmospheric pressure, and that is why we can answer this question that the standard boiling point is slightly lower than the normal boiling point. This is how we understand. Now, my dear students, please remember that the normal boiling point of a water, that is at 100 degrees centigrade temperature or 373 Kelvin, whereas the standard boiling point of water is 99.6 degree or 372.6 degree. At temperature altitudes, at high altitudes, my dear students, the at high altitudes, atmospheric pressure is low. You know, as you go up, the layers of air become lower and lower, and in that case, the atmospheric pressure become low because low amount of air is available on that particular surface as compared to the sea level. So at high altitudes, atmospheric pressure is low. Therefore, liquid at high altitudes boil at lower temperature. You may be asked this question as a give reason, that why liquid at high altitudes boil at lower temperature. So at high altitudes, the atmospheric pressure is lower than 1 atmospheric pressure. So liquid can easily boil at lower temperature, and their vapor pressure is equal to outside pressure or atmospheric pressure at that time can be reached easily even at lower temperature, and that is why these liquids can boil even at lower temperature as compared to the sea level. Thus water boils at lower temperature on hills. Now, my dear students, we have one more reason or scientific reason to discuss, that give reason why pressure cooker is used for cooking food. You know, my dear students, that when we use pressure cooker, because in pressure cooker we have closed the cooker, so it's a closed vessel, the external pressure is increased to high, because by closing the pressure we put weight on it, and that is why this weight provide extra pressure. thus boiling point of water is increased. The extra weight that we put on cooker, which we call it as a whistle or CT, that actually increases the external pressure, and that is why inside the cooker the high temperatures are generated. The temperature even or the water boils at more than 100 degrees centigrade temperature, and that is why the food is cooked faster, because the temperature inside the cooker is much higher than the temperature into the open vessel, because in open vessel we cannot maintain the temperature more than the 100 degrees centigrade, and that is why the cooker cooks faster as compared to the open vessel, my dear students. One more reason that in surgical hospitals the instruments are sterilized in the autoclaves. The instruments are sterilized in the autoclaves because in autoclaves boiling point of water is increased by increasing the pressure above the atmospheric pressure by using weight covering the vent. Again into the autoclaves. Autoclave is a kind of machine in which the various instruments for surgery are sterilized. Sterilized means made germs free. To make them germs free, they are boiled. When they are boiling into the vents of the autoclave, the area where the instruments are kept, and they are boiled with the water. Above that, the pressure has been increased, and as the pressure is being increased, the water boils at higher temperature than 100 degree centigrade temperature, and that is why a huge temperature is generated, and that is why all the germs can be cleaned, can be killed. Then we have one more question to study, my dear students, that what happens when liquid is heated in the closed vessels? That I think we should discuss into the next class. So my dear students, whatever we have studied, just let us look at the different things that we have discussed today. Let's pay attention to and let us revise what we have studied today. Today we have started studying about the vapor pressure. You can see that if you fill the liquid into the closed container, it vaporizes. It exerts pressure on the wall of the container as well as on the surface of the liquid. The vapor pressure becomes maximum when there is an equilibrium between the vaporization and condensation, and that is how we get a maximum vapor pressure, which is a constant vapor pressure. Such constant vapor pressure or maximum vapor pressure is known as the vapor pressure at equilibrium or saturated vapor pressure. If we heat the liquid into the open vessel, then the liquid can move away. The vapor can go outside and exert the pressure on the liquid. When the pressure of the vapor is equal to the atmospheric pressure or the outside pressure, the vaporization starts even from the bulk. Actually, vaporization is a surface phenomena that takes place only on the surface, but uh, by increasing the temperature, the vapor pressure increases, and it increases to such a high level that in bulk also the vaporization start. When the vaporization start into the bulk, we call this temperature as a boiling point, and we call this process as a boiling. So the temperature at which the liquid start boiling is known as the boiling point. Boiling point are of two types: normal boiling point and standard boiling point. When we have the outside pressure is 1 atmosphere, it is called the normal boiling point. But when we have the outside pressure equal to 1 bar, such boiling point is known as the standard boiling point. And then we have studied the various reasons that can be asked into your exam, that standard boiling point is slightly lower than the normal boiling point because